actually cooking. Here it is. All right. So we are talking about threads, right? All right, good. Threads are fun. So we'll do it in. We'll do it inside this class. What's this guy called? Is this our? Is this one? Yep. Okay. So what I'm going to do is I'm going to go ahead and well, last time we talked about interfaces a little bit, right? We talked about threads. We talked about well, let's just got to go through our couple things we mentioned last time. So we were talking about communication. We talked about inter-process communication type stuff. So one of the issues being like, I'll probably use the McDonald's example. If two people try to run up to the register at the same time, and this kind of goes hand in hand with these multiple types of communication. And if you were at the senior seminar presentations yesterday, there was a weird debate that happened between two of the things talking about this very topic. And one of the students who should know better had quite a bit of asynchronous communication in his project and was having issues with data not being available when he needed it to be available, for the exact same reason that we talked last time about asynchronous communication, doing things on its own, not blocking, so the rest of your program can keep cooking. So if on the very next line you try to use the data that's being retrieved or calculated over here, it might not be ready for you. It's not done cooking. We can't sit down and eat the lasagna until it's done baking. We can try. Okay. I like that Cookie Monster commercial. Have you seen that one with Siri? Yeah, he's Cookie Monster wants Siri to set the timer. And he's waiting for the cookies. He starts eating utensils and stuff. And he's like outside peeking through there, and it looks like he's probably spent like a half hour waiting for these cookies to bake. And he tells Siri to check the timer. It's been like 40 seconds. Very impatient. Love Cookie Monster.
Is Cookie Monster still a thing? I heard they changed it to the vegetable monster. Like on the show.
Oh, they can't do that. That's not right. Does anybody know? Cookie Monster has to be a thing. He's in all these commercials. Huh? Oh, the Veggie Monster? Yeah. He got cut. It was a tryout. Kicked him off the team. Yeah, it's like saying Big Bird gets turned to Normal Bird, so you don't maybe have people making fun of big people. Yeah, seriously. You play a pretty good Big Bird, actually. All right. So we started talking about the thread class, and the thread class implements this interface called runnable. And we looked at the runnable interface, and all the runnable interface dictates is that we have a single function called run that returns nothing. It must be public, and that run method is the magical method that, well, is the method that gets called by our magical method that comes with the thread class called start, that knows how to talk to the virtual machine and spin off a new thread and do all the things that new threads can do. That is running parallel to our existing program. So our existing program runs in what we would usually call the main thread. All right. And so anything we want to happen simultaneously that is non-blocking is going to have to run on something other than the main thread. Now, so we have, let's say we have 5 or 6 threads running along, and we're claiming that these guys are running at the same time. Well, an accurate claim is that they're not blocking each other. Okay, so from a logic perspective, these guys are not blocking. Now, whether or not they're actually running simultaneously or just look like they're running simultaneously is a different story. When we deal with threads, or the old school version of this was processes, you have these multiple things running on your computer at once. So for instance, you have Microsoft Word open and you also have Chrome open at the same time. These are 2 separate processes on your computer. The reality is each of those probably spawns off a couple of threads. So for example, if you have one web page loading in Chrome and you open up a new tab, you can do that, right? While a page is loading, i.e. not blocking. Right? So each of your tabs are probably running inside of their own thread. then the application itself is running inside of the main thread for that application. That way you can still click around on the application while your different tabs are doing different things, that kind of stuff. So most of our applications today have several threads associated with them. But even if we just dumb it down and say that there's one thread, one process for Chrome and for Microsoft Word, for example, we might believe that both of those guys are literally running simultaneously. And in today's computing world, there's probably a large percentage of the time truth to that, because we have multi-core processors now in our computers, right? We have dual core, and then even within the dual core, they all have hyper-threading, which is like, the dual core is 4 logical cores, whatever the heck that means, that uses something called pipelining to sort of kind of fake it running a little faster. This machine's a quad-core processor with hyper-threading, so there should be 8 logical cores, whatever. So if we just say a quad-core processor, that means theoretically it can do 4 things at the exact same time. Each of those cores is a processor in and of itself that can handle the magic tricks that a CPU knows how to do. So that means Microsoft Word could be running on one processor, Chrome could be running on another processor, and those guys are actually doing things at the exact same time, because the magician that's performing the magic tricks are 2 separate guys. Okay? But now, historically, when we had single-core CPUs, you could only have one thing actually happen at the same time. Now, computers are really, 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 really fast. So we're not going to notice. One of the jobs of our CPU in our computer is to fake the end user out. Make us believe that everything's happening at the same time. So even if you have a single core processor, which a lot of the lower powered laptops and stuff like that have, like Chromebooks. Actually, Chromebooks are probably running dual core Atom processors now, but roll back 4 years, they were probably running single core Atom processors. But whatever the deal is, chances are a modern processor at its current speed, as fast as they are, even if it's running on a single core, probably will keep us faked out enough that we're not going to complain, unless you're trying to do crazy stuff like Photoshop and playing a video game at the same time and rendering video all at the same time. You're probably going to notice your video game is not going, you're going to get like the half a frame a second type of, and if you've ever tried to play a first-person shooter at a half a frame a second, it does not degrade my quality of gameplay at all. It doesn't make it better. I'm just less aware of how bad I am. Yeah, my real sport is beach volleyball. All right. So, huh? No, I scored like 290 of them. Yeah, we had some weak spots on the team, but the other team was substantially weaker, thanks to you and the rest of the team. All right. Plus, I was a cheerleader. I cheered for whether we won the point or lost the point. I berated the other team and my teammates when we lost. I just cheered myself when we won the point. More than likely, I was involved. Not for... all right, so when we create multiple threads, all we can guarantee is these guys are not blocking each other. We can't necessarily say that these things are happening at the same time, because they need to be scheduled on the processor. Things get even weirder with Java, because your Java program is running inside of a virtual machine. So your Java virtual machine, if we kind of look at the lay of the land with this, we have our actual, we'll say CPUs, whether it's 1, 4, whatever. So our actual CPUs. Sitting on top of that, we have a computer program, no different than Microsoft Word or Chrome, called the Java virtual machine. All right. So the Java virtual machine sits on top of that. So, if the Java virtual machine spawns off multiple threads at its level, those multiple threads might get processed by multiple CPUs. But the virtual machine itself is then going to run your program. So we'll call this guy driver.java. That guy. All right, that's the program he's running. All right. Now, if our driver.java spawns off a couple of threads, be a thread. And obviously, threads are orange. All right, so this guy spawns off a couple of threads. These threads, so now you kind of have 3 threads involved here. You have the main thread associated with driver.java, plus these 2 additional threads that driver.java spawned off, created instances of threads, called the start method. The start method did whatever magic was required to talk to the virtual machine and said, hey, give this dude a couple of extra threads. But now we're at the mercy of how this Java virtual machine schedules these threads. How does it schedule them to who runs simultaneously, who doesn't? Can both of these threads actually do something on the fake CPU? Because the Java virtual machine is a computer built in software. So this guy has a fake CPU, which then has a translator between it that interprets from this guy to a single instruction on the CPU. So we don't necessarily have a whole lot of control over when our threads are actually getting CPU time and things like that. So a common misconception is that multi-threading improves performance. In fact, in some cases, it could degrade overall performance because there's got to be some level of management that's occurring to keep all the threads in order and know who's getting CPU time. And we've complicated the problem, right? We're probably not going to notice, but I don't know if I've used the example in here before. Did we have a conversation here about whether like a quad-core processor is always better than a dual-core processor? Okay, well, what do you think? If you you're getting a new laptop, do you get the quad-core processor or do you get the dual-core processor? Go ahead.
Isn't more cores better for like graphic-intensive applications?
Okay, there's truth to that, but why?
Well, aren't certain applications only available or able to access or utilize them among the cores? Like the Mac Pro's 12 core isn't as good as a 6 core, depending on what you use it for.
Okay, well, I think it's depending on what you use it for is certainly a truth. So, the example I often will use, so let's take it to real life first. If I can change a light bulb at 4 gigahertz and the rest of you, how many people, let's just take it, so 1, 2, 3, 4, 5, 6, 7, 8 here. This half of the room is an 8-core processor, top dollar, okay? And each of those cores can change a light bulb at 2.9 gigahertz. And now we're going to have a light bulb changing contest. We only have to change 1 light bulb each. Who's going to win? I'm going to win. It's like I'm the fastest. And a light bulb is a one-person job. So
doesn't the gigahertz go down as the cores increase?
Not necessarily. And gigahertz is a bad way of comparing processors because 2.9 gigahertz from this year's processor doesn't equal 2.9 gigahertz from last year's processor because last year's processor has less magic tricks in those. So gigahertz is typically the how many billions of instructions can occur per second. That's the idea of it. But some instructions are more powerful than other instructions, so you really can't compare gigahertz directly. So unless you're comparing the same architecture. So when I'm saying this 8-core processor versus the single-core processor, we're on the same architecture. All right, you guys don't have some sort of, extra powerful version of changing a light bulb where, yeah, you can do it at 2.9 gigahertz, but it takes less physical movement or something, whatever. All right, so in a job like that where we're changing a light bulb, more cores is not better. So if that's all you're doing, having the multiple cores isn't going to benefit you. Now, the example I like to use with college students, because none of you, I'm assuming, have ever stolen a movie and had to convert it to a different format. So if you download an hour-and-a-half movie off a perfectly legitimate site, I'm assuming, and you need to convert that into a format that will play on your Xbox or Apple TV, whatever it is, because you probably got it in some weird Russian format from your legitimate site, of course. If that's the case, and you need to convert it on your, let's say, your reasonable laptop, we're not talking about a crappy laptop, but a dual-core 2.2 gigahertz laptop, how long, and I realize this is going to be a guess, because none of you have ever done this, but how long would it take to convert that video? on a laptop, you think? At least 30 minutes, maybe 45, an hour, or something like that. If you have one of the really portable laptops, like a MacBook Air or something like that, could be taking an hour and a half, 2 hours, long time. How long do you think that same video would take to convert on our, we actually have like the cheapest Mac Pro, the one with the least number of processors. I think ours only has 8 processors in it. How long do you think it would take to convert on that machine? Way less. Probably like 2 minutes. Okay? Maybe 3. Maybe 3. So a lot faster. So that's the type of job where you can divide it up among a whole bunch of those processors. That's kind of like cleaning up a park. You know, converting video, you can do portions of that video. So you can have 8 different processors, each working on 1/8 of the video. And it's cutting the amount of time down by, 8 times. Those are Intel Xeon processors that have hyperthreading. So even though it has 8 processors, it's got what's called 16 functional processors especially for video conversion. So you can divide the amount of time by 16. So if it would take 60 minutes divided by 16, that's just under 4 minutes to convert that same video. That would take an hour on another machine. But that would be on a single core machine, but whatever. A lot faster. So that's where multiple cores really comes into play. If you are a gamer, you play a lot of video games, you would probably be better off with, if you were comparing a dual core processor with a higher clock speed, say 4 gigahertz, compared to a quad core processor with a lower clock speed, 2.2 gigahertz, you'd probably be better with the dual core. You still want the multiple cores because most video games do take advantage of multiple threads, but basically a majority of the stuff that's happening in the game is going to happen on one of those threads, maybe 2. The other stuff is kind of extraneous stuff happening in the background. You're not going to notice performance-wise that difference, but what you really want is the quad core and spend the extra money to get the super fast quad core. What's the slogan from the American slogan from the movie Contact? Why build one when you can build 2 at twice the price? You see the movie Contact? It was a good movie. They got the Arecibo, and they had the radio telescopes. They got the alien signal. They had instructions for building the death machine. And so they decided to do a worldwide thing to build it, but then the Americans built their own version. Why not? Worked out well for them. All right, so that's kind of the concept of threads, but things get a little bit weird with the virtual machine because we're kind of at the mercy of how the virtual machine actually schedules our threads for his fake C processor, which then is talking to the CPU under the hood. And is this just one of our CPUs, or is this a dual core CPU? Is this a quad core CPU? And how well does the virtual machine schedule for that guy? Well, actually, it's the other way around. How well does the CPU schedule for this virtual machine? Does it treat the virtual machine as a high priority process that is getting extra CPU time? Like a system backup or something like that might be, but who knows is the punchline. We don't have a whole lot of control over it. So back to the original question was, is more threads necessarily better? You're not going to improve the speed of your application just by adding threads unless you have reasons for adding threads. That is, if you have non-blocking reasons. So in our case, we were thinking about merge sort. We're not actually going to write a multi-threaded merge sort because that would take quite a bit more tools in order to do this. But since we've identified a problem that could be solved using multiple threads and would benefit from multiple threads, just like the video conversion example, merge sort will work similarly to that. In that case, we would probably be benefiting ourselves by multi-threading that application from a performance perspective. If you're only sorting 10 things, don't waste your time. But if you have 10 million things, you might start noticing the performance difference. But we're going to start off today just visually experiencing how those threads are scheduled. So we're going to build ourselves a thread object. So we're going to create our own object that is a thread. It's going to extend the thread class. And then we're going to write our own little version of the run method. And all this guy is going to do is he's going to count. All right, he's going to count from, just indefinitely, 1 to 1 million or something like that, and print it out each time. And what we're going to see, these two guys are going to be running at the same time, and the parent is just going to be sitting there. And the children, you're going to see, I'm child 1, and I'm counting 1, 2, 3. Then you'll see child 2, 4, 5, 6, and sometimes you'll see child 1 interject in there, a single line. So you're going to kind of get to see how those threads are actually being scheduled at some visual level. So I'm going to go ahead and create a new class. And we're going to call this guy WorkerBee. So he's going to be our WorkerBee class. And we're going to say that this guy extends thread. Okay, now remember, all programs begin and end with main. This class, this object that we're creating here, is not going to have a main in it. He's going to be reliant on our driver class to create instances of him. Okay, just like the string class that we've used a whole bunch doesn't have a main in it. You don't just run the string program. You use strings in your program to solve problems. We're going to be using WorkerBees to solve problems. All right, so this guy is a thread, and right off the bat, we have to, since this guy implements runnable, we have to go ahead and write our public void run method. And we'll just start off by, let's do, well, I from a thread. And I think we could do this dot. That'll be good enough. This will be the name of this thread. I think it gets some sort of weird scheduler name, but this will be good enough for our quick little example here. And then let me just empty out main. So we're going to go ahead and create an instance of our WorkerBee, just like we create instances of any of our other objects. Like we've looked at the random class, we'll say WorkerBee, the type, WB1 is equal to new WorkerBee, just like that. So there's our first WorkerBee. We'll create a second WorkerBee. WB2 is equal to new WorkerBee. Now if I were to do a system.out.println WB1, what do you think would print out, Tyler? Since we're not going to have your presence on Friday. What's going to print out in this program right now? This has nothing to do with anything I've taught today. This has everything to do with things we've taught over the last month. Well, I'm printing stuff, so something's going to print. Something's going to print right there. What is this guy going to boil down to? What will that variable boil down to if I try to print it? Remember we looked at the Java documentation and we saw there's a whole bunch of versions of println. One for ints and chars and objects and strings. Well, this guy's not an object, or I'm sorry, he's not a string. He's not a char array. He's not on any of our ints or anything like that. He's a WorkerBee, and a WorkerBee is an object. What does println print out for objects? Okay. When in doubt, you say crazy memory address. Rule of thumb. So it's usually when I'm asking you what's this going to print out, it probably is leading you down a path of having you decide whether this is going to actually be something with logic behind it, or is this the catch-all memory address? So this is going to be our memory address. So there's our memory address, and notice this guy is a thread. Actually, it isn't quite a memory address. This guy is that they must have implemented a toString inside of the thread class. So if we came in here and we said public string, well actually it's going to be the thread. I'm not going to waste my time doing it. It's not going to help us in this case. All right, so actually this printed out WorkerBee's toString, which actually was thread's toString, which decided it was going to show the name of that thread instead of the memory address, which then overrode the memory address version that it inherited from the parent. Now let's go ahead and tell each of our WorkerBees to start. All right, so we created two WorkerBees. These guys are threads. we went ahead and did our due diligence by writing the run method that we're supposed to write. Then we're telling each of these worker bees to go ahead and start, which is doing the magic behind the scenes, telling the Java virtual machine here to go ahead and spawn off 2 threads. All right, and when we start those threads, what does it do? It calls each of those threads run method. And what does the run method currently say to do? It does exactly one thing, then ends. Print out hi from a thread, and then the thread's name. All right, so we'll go ahead and run this guy. So we should see 2 things printed out. From our perspective, it might not seem like it's being run in any sort of magical way. We might as well just printed it out right here on the inside of main, but it's actually coming from 2 separate threads. Hi from a thread, and this guy's thread 0. Hi from a thread, this is thread 1. Okay? Now, what we're going to do is we're going to create a loop in each of our threads. That's going to go through, and we'll use this .name since that gave us a pretty decent thing. So we're going to say for int I is equal to 0, I is less than that's 1,000,000. That's 1,000,000,000. And we'll say system.out.println this dot get name concatenated with a space. I'll put a little arrow in there. It'll look legit. Concatenated with I. So each of our threads is going to go through and count from 0 to 1 billion. That should take enough time for us to recognize this for a while. Is it 10 billion?
It's 10 million.
10 million? Oh, I stopped at 1,000,000, didn't I? Oh, there. Well, that should be plenty of time too. That's 100 million. That's 1 billion. We're good? All right. So this will go through and it will print out, and I/O is expensive, so this is not going to run all that quickly. We could probably leave this running through lunch and it won't finish because of the number of times it's writing stuff out, and it's doing this for 2 separate threads. All right, so when we see the output of our program, what we're going to see is we're going to see both of our threads competing for CPU time. But both of those guys are going to be writing out to the same terminal. So we'll see some thread 0, 4, 5, 6, thread 1, 8, 9, 10, so on and so forth. And we'll see those guys kind of mixed together. So we're going to be able to visually see how these threads are being scheduled. Make sense? And I think if we want to, all right, so we're kind of seeing how this is working. Generally speaking, it's kind of happening in batches. All right, so one's getting quite a bit of CPU time there. A lot of CPU time. All right, and then we could certainly create more worker bees and have these guys competing. What I want to do here is let's go ahead and see at what point we have a noticeable slowdown. I equals 0, I is less than, let's start with 4. We'll create 4 worker bees, I plus plus. And I'm going to go ahead and we're going to create a variable for holding on to our worker bee up here. And then we'll say WB is equal to new worker bee. And then we'll say worker bee start. So this is going to go through and create 4 worker bees, temporarily storing it in WB, telling it to start, and then we've lost access to that guy from main. Those threads are still running, but we don't have any way of communicating with them from within main here. This is more just to see a performance. All right, so now we have 4 different guys competing. Okay, so these 4 threads are all running at the same time-ish. Change this to 8. All right, so now remember when we talked about this for our merge sort, we talked about we have a problem of being able to communicate stuff between our threads, right? All right, so here, let's pump this up to 80. So we have 80 little worker bees. They could be each working on a portion of our, now what'll be interesting here is let's kind of stop it. All right, so thread 6 is at like at 1400. Yeah, they're all kind of keeping up with each other, it looks like. Or 14,000 rather. It's not really slowing down. Huh?
Are some of the numbers out of order?
Well, it's not that they're out of order. That's the number for that particular thread. Yeah, I mean, they will be out of order on the screen. Thread 0 might be at a different count than thread 8. Yeah, so we might see numbers go out of order in there because, thread 0 might have gotten 40 CPU cycles in a row before thread 8 ever got back and was able to pick up where it left off, because each of these guys are on their same counter, as opposed to having a global counter that they're all operating off of. So let's actually look at that. So I'm going to create a new class. I'm just going to call this guy core. And I usually refer to this as something called a singleton. We talked about singletons? Okay. We've talked about design patterns. New phrase as well. Okay. All right, so we have this idea of something called a design pattern in computer programming. And are you sure we didn't talk about design patterns? No, it doesn't look like it. Okay, that's fine. So, design patterns, and it's actually, this is kind of a popular interview question when you're talking about getting a software job or something like that. Design patterns sound complex, like it sounds like it might be something formal, and all this is a proposed, quote, good solution to a, quote, common problem. All right, so academics love these from a research perspective. All you have to do is the requirements for a design pattern are funky name, quote, common problem. What's a common problem? Well, it depends. If you're a rocket scientist for Lockheed Martin, a common problem might be fuel consumption for a rocket. All right, well, if you're a iPhone developer, fuel consumption for a rocket is really not on your radar. So you could that guy from Lockheed Martin can write a design pattern called something funky for fuel consumption and what's the best way to calculate fuel consumption at the software level, whatever, for rockets. So you can pick a common problem. And then also, what does it mean for a solution to be good? Well, the starting point is probably it must be accurate, but kind of good's in the eye of the beholder. We've recently talked about big O notation in terms of it's kind of a number we put on an algorithm in terms of its relative performance. I like to think of it in terms of the number of questions we have to ask related to that algorithm. Well, with that in mind, a good solution might be, through some people's eyes, a smaller big O value. N log n is better than n squared, for example. But that's not necessarily a truth, right? Depends on the application. Sometimes we're not going to notice the difference between n log n and n squared. And if the n log n solution is basically like reading stereo instructions, and the n squared solution is very easy to follow and manipulate and repurpose for different things, that very well might be the better solution, right? If we're not going to notice the performance difference. All right, so basically good solution can mean anything. That's accurate. Common problem could literally mean anything. All right, so design patterns really mean, it's almost like hocus pocus. It doesn't mean a whole lot. So we can literally have an infinite number of design patterns. Every day somebody just come up with a new made up design pattern that solves some sort of common problem. And it doesn't always have, well, it does apply to software in practice, but it doesn't have to. For instance, we all have design patterns that we have in life. So for instance, the one I like to use is opening a banana. Okay? There are 2 accepted practices for opening a banana for human beings, right? Most human beings grab the stem and snap it off and open the banana that way. Okay? The smart human beings, okay, probably not you.
How do you go from the bottom?
You do? Okay, tell me your technique.
You like flip, rather than go from the stem, you flip it around.
Okay, I got that's the bottom. Okay, I'm with you.
So you squeeze it and pull it.
Oh, see, so you've observed monkeys in the zoo.
Monkeys eating bananas.
If you ever watched a monkey in the zoo eat a banana, that's what they do. They pinch the end of it and then it just pulls apart. Like it's like a non-issue.
And you don't get any of the string stuff that sticks to it.
Right. Now the gorillas,
They just
they snap the thing apart and like squeeze it and then start throwing it at people. It's awesome. Okay. That's not a widely accepted practice for humans. Should be. Should be. I mean, it's efficient. Yeah, what? It's definitely efficient. All right, so that would be how to eat a banana design pattern. And we probably would come up with some stupid name for it, for each of those. Okay, so the monkey method and whatever. So those would be design patterns. Now, so we could have an infinite number of design patterns, but there are some popular design patterns. So these are design patterns that have kind of risen to the surface as being widely used, widely accepted throughout in the reality, computer science, software development. So the 3 that I like to introduce are MVC, Observer, and Singleton.
It just sounds like a fancy, like British name.
What?
Singleton.
Singleton? Really?
I think so.
Well, I guess that could be somebody's name. Yeah. At first, it seemed like a stupid comment, but I get where you're going with it. Yeah. All right. So let's just give a high-level definition of each of these. MVC, this guy stands for Model View Controller. Yeah, so I said they have to have like weird names. This guy even shortened his name, turned it into an acronym. So MVC stands for Model View Controller. So clearly that's we all know what that means just by its name, right? Generally speaking, what this basically says is it's a good idea to keep your interface stuff in one place and your logic in another place and your data in another place. All right? So if you are writing a software application and you have your user interface, make the stuff that makes it look pretty, then you have your logic, the stuff that makes it work, and then you have your data, the stuff that is all based on, your database somewhere. It's a good idea to keep those in 3 separate places and then have interesting ways of bringing them together, right? Rather than, and really where this was born is we had an older technology called PHP. And early day PHP, which is a web technology, you would have your HTML that made your website, that's your interface stuff, right? You'd have that in the exact same file as your PHP code, just kind of hodgepodge together. Now, in the early days, when PHP first came out and websites weren't that complex, that wasn't the end of the world. You didn't have that much HTML code. We didn't have all that, the interfaces weren't that fancy, that kind of stuff. But as soon as our websites started becoming more and more complex, if you look at, you do a view source on like MSN or something like that, it was like thousands of lines of HTML code in there. So if you had your PHP logic embedded in there somewhere, it would be very difficult to manage that site, right? You really want to pull those 2 apart, so when you need to make tweaks to the way your page looks, you change the HTML file. When you want to make tweaks to the way your page works, you make tweaks to the PHP file. Sometimes you then need to connect those 2. If you are going to put a new drop down over here, you probably need to fill that drop down with some logic, which then also needs to talk to your database to get that data that's going to fill in there. Maybe it's sports scores or something like that. All right, but that's MVC. And each of these, so one thing we want to consider about design patterns, these are ideas rather than implementations. All right, so pretty much every modern development technology has their own take on MVC. Okay, if you're going to write a Swift application with iOS and Xcode.
11:50, we got on class.
That wasn't your little yelling.
Class is over.
So let me just finish this comment. So so Xcode, for example, has its own take on MVC. Here's the way you accomplish having your interface in one place, your code in another place. Using Xcode, you do it the Xcode way. Android Studio has its own approach, so on and so forth. All right, so we will pick up here next time, finish talking about design patterns, and also talk about the final exam. No homework.